Welcome back. Up until this point, we've been focusing on electric forces and the electric field. Of course, in addition to forces, one of the most important topics in physics is energy. And so today we're going to talk about the energy that's associated with electricity. You'll remember that conservation of energy is one of these topics that we spend a lot of time talking about. And there are many ways that we write down conservation of energy. We've written down conservation of mechanical energy, conservation of total energy. I'm going to start today with the expression for the conservation of energy in the presence of just conservative forces. So if a force is conservative, I'm able to write down the work due to that force in terms of a potential energy function. And this is something that you spent a lot of time talking about last year, that if I have a conservative force, a lot of interesting things come along with that, right? For example, if I move things around due to a conservative force, then the only thing that matters is where I start and where I stop, right? The force is path independent. That's what makes it conservative. So the electric force turns out to be a conservative force. And I can show this by eventually getting to the point where I can rewrite this force as an expression that has to deal only with a associated potential energy. So let me rewrite this just a little bit and say, well, in the case where I can define a potential energy, the change in that potential energy is going to be equal to minus the work done by the force, which in a general expression is minus the integral of that force. In this case, it's going to be the electric force, dotted with the displacement, that is, dotted with the parameterization that the force takes. Okay, so let's do it for a simple example. If I have two charges, I have some fixed charge that I'm going to call capital Q, and I have some test charge that I'm going to call little q. And of course, I'm going to be studying the test charge, right? That's what we've been doing the last couple of weeks. So what happens when I move that test charge around? Or in other words, what is the work done by the electric force as I move that test charge around? Well, I know that the electric force is just going to be 1 over 4 pi epsilon naught, the product of the two forces divided by r squared in the r hat direction. And I can already see that the force itself only is in the r hat direction, which either points, r hat points away from q, but it's only in the radial direction with respect to big Q. And therefore, if I'm trying to find out if there's any contribution to the work, if I'm trying to find out if there's any contribution to this integral, then the dot product between ds, which is a little bit of my motion, a little bit of my parameterization, and the force itself, that dot product can't be zero. That is, I won't have any contribution to the force unless my two charges are moving away from each other or towards each other. And so it doesn't matter, I already can see it doesn't really matter how I move in the angular direction. If I'm moving towards or away from the charge, that's when I'm going to have a contribution. To this integral. Of course, S is going to be the path that I've chosen for my charge to make, which I'm showing in green here, where some tiny bit of the path is the thing that I'm going to call ds. Well, since I've already seen that the only part of ds that's going to matter is the part in the radial direction, then I'm going to actually say, well, the only part of ds that I care about is going to be some little bit in the radial direction times r hat. Okay. Now this thing here basically says that my ds is only going to be in the direction of outward from big Q. Now, I can do this integral, right? It's actually not such a bad integral. I can plug in the expression that I have for the force. I can dot it with ds. I have to remember that r hat dot r hat is equal to 1, right? Because this is the r hat is the unit vector, and so the unit vector dotted with itself is the magnitude of 1 times the magnitude of 1 times the cosine of 0, which is also 1. And when I finally finish evaluating this expression, I can see that I can write the change in potential energy, the final energy minus the initial energy, in terms of a single function, right? I have QQ over 4 pi epsilon naught, 1 over some distance. And so from this expression, I can define u as a function of r to be q over 4 pi epsilon naught 1 over r. And then then what I found by doing the integral out in all of its glory is just that uf minus ui is u of rf minus u of ri. To put this in a more philosophical point, what I found out is that I can represent this work integral, that is, I can represent the integral of the force over any displacement, as a single function that only depends on where you are, right? And that gets us back to this idea of the definition of a conservative force. I can write the work done by this force as a change in potential energy, where that potential energy is just a function of where you are, not how you got there. Now, there's a fun example that we can do with this. So consider the situation where I'm trying to build up a universe full of charge. Okay, so the first step is to find just a single charge, which I'm going to call Q1. And I want to know, well, how much work, how much energy is it going to take to bring that charge in from infinity and place it somewhere in the universe? Well, nothing, right? There are no other charges. In the absence of this charge, there are no electric fields, there are no electric forces, and so the total energy at the end of this configuration is equal to 0, because I don't have, it didn't cost me anything to drag that charge in from infinity and bring it to this point. Once I bring my second charge in, so I'm going to call that Q2, now I have to be a little bit more clever, because when I bring that charge Q2 in from infinity, I now have another charge in the universe. And so I have to worry about, well, how much work did the electric force do to Q1? How much work did that cost for me to bring Q2 in from infinity? Well, luckily I have an expression for that. I know what the final potential energy is in this case, right? It's just Q1, Q2 over 4 pi epsilon naught, 1 over, in this case I'm calling it R12, right? I know where Q2 finished, and since the electric force is conservative, I can calculate how much energy it took for me to get that Q2 from infinity and drag it to this point. And it's now a good time to point out that all of the signs here are sort of taking care of themselves, right? How much work the electric force is doing, well, sometimes it could be positive, sometimes it could be negative, right? If Q1 and Q2 have different signs, bringing them closer together is actually going to be at a lower potential energy, because those charges are going to want to come together, right? It's not going to, the electric force is going to give kinetic energy to the system. It's at a lower potential energy. If Q1 and Q2 have the same sign, it's going to be hard to bring those together, and so I'm going to have to add some external force in order to overcome that. But I'm going to a final state of higher potential energy, and so all of the charges have worked out. This is, of course, a consequence of the fact that I did the calculus carefully, and by doing the calculus carefully, I keep track of all of the charges, all of the signs involved. Well, if I keep going with this and I try to bring in charge Q3 from infinity, well, now Q3 has to deal with overcoming two different electric forces, right? There are two forces doing work on Q3, and so I need to know the final potential energy for Q3 depends on Q1 and Q2, which is going to depend on, well, how far away is R3 from Q1, and how far away is R3 from Q2. And so then the final energy in this case is going to be, let's see here, it's Q1, Q2 over 4 pi epsilon naught, 1 over R12, plus I have all of these combinations here, Q2, Q3 over 4 pi epsilon naught, 1 over R23, plus Q, let's see, which one? I have 1, 2, 2, 3, I need 1, 3 over 4 pi epsilon naught, 1 over R13. Right? And so you can see every charge I add in has to care about all of the other charges involved. But I can actually write this in sort of a compact way, that the total energy then is going to be the sum over all possible pairs. So I start with, I have one sum that goes over all of my particles, and then of course the second sum tells me that I have to pair that particle with every other particle, every other charged particle, but the k not equals to I, I'm sorry, this should be j not equals to I. The j not equal to I reminds me that I don't count the electrical, the potential energy that a charge has with itself. Okay, that's what potential energy is. But of course, we spent the whole last lecture talking about trying to come up with some description of the world, not caring about the test charge. And so we have to ask ourselves, if I was able to take the electric force and rewrite it as the property of the universe at some point times another quantity, which we call the electric field, can I do the same thing with the potential energy? That is, can I talk about what all of the other charges in that sum are doing and not care about the particular charge that I'm interested in until I put a charge there? Let me say that yet another way. If I look at all of the charges in the universe, do they set up some description of what's happening anywhere in the universe before I put a charge there to experience it? Before I actually have a potential energy, is there a way for me to tell what the potential energy of the system is when I bring in a charge and put it in a specific location? Well, of course there is. And so I can take this description now, potential energy U, and I write it in terms of something that we're going to call V, which is the electric potential. And I've always had a bit of pause when talking about the electric potential, because the electric potential is going to be something that's defined everywhere throughout space and time. And it's going to tell me something about what the potential energy of a system would be if I were to put a charge there. Well, if something is a function of all space and returns a number that's going to be useful to me later, that's also a field, right? It's a scalar field, not a vector field like the electric field is. But this is the potential field, right? We call it the electric potential not to confuse it with the electric field, which is a vector field. But I want you to keep in mind that all of the charges in the universe define the electric potential everywhere in space through all times. And that quantity itself is an important field, right? It's a mathematical quantity that's associated with a field. And we're going to do more examples of the electric potential in a little bit, but I want to end by talking about the real importance between the two different descriptions that I have. Potential energy is always the integral of a force along some path. And I can calculate the potential energy of a system of charges, say, by pulling all of these charges in from infinity and counting up and counting all of the energy associated with the final state. The electric potential includes all of the same information except that final charge. It says, what is the property of space at this location that will eventually allow me to calculate the electric potential energy associated with this charge distribution. So we're going to do more examples of electric potential in the upcoming days, but I want to leave us with one last calculus fact, and that is, right now I have expressions that tell me that the potential is an integral over the field, right? The electric potential is an integral over the electric field. If I differentiate this, I actually end up with an even more useful expression, which tells me that the electric field is related to the derivative. For example, in the x direction, the electric field is related to the derivative of the electric potential.